So that's the hash functions. Even though we have a good hash functions, they are surjective functions. This means that there is a collision happening here. And this number of the collisions can be represented by load factor. And load factor actually often determines the hash table performance. Load factor is very simple. N is the size of stored entries, and S is the size of hash table. And yeah, it's just how much is being occupied. Why is it important? Actually, it is very important to the quality of the hash function, uniformity. So, for example, if hash functions are uniform and it just adds up things, then this load factor can be 1 eventually. However, if hash function is not uniform, and if a certain index is never being used, never come out from this hash function, it's never going to be 1 eventually. So if hash function is good, then this load factor can be very increased. Having said that, a high load factor is much preferable. Actually, it's not. High load factor means that higher chance of the collision, right? If it's uniform, it reduces the collision. But still, if it's going to reach to the 1, then it's very high chance of the collision. In that case, we have to resolve this collision and that cost is high. And because of that, we want to have a low value of the load factor. And to have a low value of the load factor, we are doing like 2 things. First thing is that it's being to resolve the collision, we are doing close addressing. That's one way of resolving the load factor issues. And the other thing is open addressing. It doesn't resolve the load factor issues, but it just resolves the collision issues. Okay. So let's look into more further in the close addressing and open addressing. Okay. For example, if this guy occupies the array index of 50 and key 2 comes in and my index is 50, and where I supposed to go? You are already there, and can I just remove you? Of course you can. You cannot. Why is that? Because this information can be valuable, so we cannot just remove it. So we have to store it somehow here in the table with alternatives. And collision resolution by close addressing is this. So collision resolution by the closed addressing is called separate chaining, and it's more like living together approach. So here, rather than just putting this one's information in the entry, it just holds the head of the linked list. The head of the linked list. So then I have the same index here. So what happens is that put yourself and my tail, and I just leave in here, so that it's being lived together approach at the same index. Here, the worst case scenario is this. Every entries have the same index from the stupid hash function. If fx equals just 50, means that regardless of the ID, then its just index will be same as 50. Then this is nothing but a long linked list, just another linked list. So we don't want that. So it shouldn't be a stupid hash function. And let's consider the load factor. Consider load factor. If the load factor is above 1, is it possible? Yeah, actually, yes, it is possible. Because that we are training so long, so load factor can be bigger. Means that every index has one or more entries. Yes. Because of chaining. Actually, then, it's just only used the linked list for each bucket. Actually, trees can be utilized. So, we can put binary search tree root here, and then we can add actually further. So that we can resolve the complexity of this side. Having said that, is this a pure hash table? Actually, it is not. It means that even with the ID and the hash function, and we retrieve the index, it does not guarantee the constant access. We still have to do some search in the linked list. But the linked list is much smaller than the just order of n, so it can be negligible, but it's not that clear because hash function can go bad. So closed addressing, actually, if there is a collision, they actually make them live together, but it certainly loses some characteristics of the hash table. On the other hand, the open addressing works like this. Collision resolution by open addressing is called resolution by proving. And proving means that seeing where is an empty bucket. I don't want to live together with you, and so I get out and I will find my own place approach. So it's all my index was originally 50, and this person is already here, so there is a collision. Here, close addressing, in the case of close addressing, this one will be linked to the next of this person. However, the open addressing approach, this one will look for another index values. There is a various method to search for an empty space with a given index. One thing is called linear proving. See whether the next bucket is empty or not. So just add one index here. So 50 is occupied, so I go to the 51. Or 51 is also occupied, and I go to the 52. That is also linear proving. That is linear proving. Okay, I go to the next bucket. Quadratic proving is a little bit different. Here we add up more like quadratic terms. So if the linear proving is just next door, quadratic proving actually goes far beyond the other places, because it has I squared term added further. I squared term added further, right? So, okay. So quadratic proving is actually, okay, I'll go to a bucket really far away approach. Then why people use quadratic proving rather than linear proving? Because that our data set is often clustered. Our data set is often clustered like these normal distributions. And if these sections share the same index, then we want to remove this frequency, move this frequency to the other side. Just going to the neighbor doesn't solve that problem. It has to move to far away. And this I squared term enables moving to far away distance, right? So that because of this ID clustering, we want to use this quadratic proving to the other side.